In this section, we're going to talk about the derivative. We kind of looked at the derivative last time when we talked about average rates and instantaneous rates of change. And so if you remember, we had a curve and a point on the curve, and we looked at that slope of the tangent line as one point moved closer to another. Okay. The definition of the derivative is given a function f of x, the derivative, which will denote f prime of x, which looks like this, is the function that describes the instantaneous rate of change for the domain of the function. Okay. F prime of x naught is the slope of the function at x naught, where x naught is in the domain of f. Okay. In other words, the definition of the derivative is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. This looks a little different than how we wrote the instantaneous rate of change last time, but again, it's the same thing. Instead of taking an x minus an x naught, we're just saying that x naught and x are h units apart, and so we're looking at the exact same picture. Okay. The main thing to take away from this is, again, it's the instantaneous rate of change. So when we're looking at this definition, you've got to remember to use the limit. Without the limit, you're looking at average rate, and that doesn't give us the slope of the tangent. That only gives us the slope of the secant. Okay. So in this section, we're going to look at two examples. And we may do a couple more, but let's start with a nice polynomial function. All of these are going to work exactly the same way. We're going to start by plugging into our formula and trying to algebraically manipulate the function so that we can actually take the limit. Okay, so if f of x is 4x cubed plus 1, our f prime of x is going to look like the limit as h goes to 0 of 4x plus h cubed plus 1 minus 4x cubed minus 1 all over h. Again, don't forget to distribute your minus sign. From there, again, we'll go ahead and simplify. So we need to FOIL out that term there. So our limit as h goes to 0, 4x cubed plus 3x squared h plus 3xh squared plus h cubed. Notice our 1's cancel out, and we get a minus of 4x cubed all over h. Now again, we have to keep simplifying because we still have the h in the denominator. And as h goes to 0, that becomes undefined. So again, we need to work to get that h out of there. So now we can distribute and combine some like terms. So notice our 4x cubes will go away. And we're left with 12x squared h plus 12x h squared plus 4h cubed all over h. Okay. Now, once we get to this step, I want to point out something. So if you notice at this point, all terms have h. Okay. This is a crucial step in your derivatives. Anytime you're asked to find the derivative by the definition, you should reach a point that looks like this. Meaning every term that's left in my limit should have an h, and in particular, I should be able to cancel that h out. So notice if I take an h out of everything in the top and divide that by the h in the denominator, I'm left with that expression there. Now, if I go and take the limit as h goes to 0, if you remember back when we started talking about limits, this is a polynomial function. And so because it's polynomial, there are no places this is undefined. And more importantly, it means that the limit is going to be equal to the function value because the function is continuous. So this tells me that I can just plug h in to my function, h being 0, and I'm just going to end up with a 12x squared. So there is my derivative for my particular function. Now again, what this derivative tells me is this is the slope of my curve. Okay. So for 4x cubed plus 1, my slope function is 12x squared. Okay. Let's look at another example. So let's look at f of x equaling 6 over x plus 2. Okay, we're going to do the same thing. We're finding the derivative using this definition. The only difference is now I'm not looking at a polynomial function. Okay. So we'll start out the same way. It's going to be the limit as h goes to 0. I'm going to plug my x plus h in there, minus my f of x, all divided by h. Okay. Now for this one, one of the things to notice is I have a complex fraction. I've got two separate denominators in there, and in order to simplify, I have to somehow get rid of those denominators. Again, one, the h, because as h goes to 0, this becomes undefined, but the others because I need to simplify. Okay. So here, we'll start by using our LCD to rewrite the function. So we'll get a 6x plus 12 minus a 6x plus 6h plus 12. Again, if you don't distribute that minus sign, make sure you insert grouping symbols. My common denominator, and then that h in the denominator, the bottom denominator, when I go to rewrite, I'm going to invert and multiply by 1 over h, so that h is going to end up in the bottom again. Okay. From here, just like my previous example, I'm going to go ahead and simplify. So my 6x's will cancel out, and notice my 12's will also cancel out, so don't forget to distribute that minus sign. So we'll get a minus 6h over an x plus h plus 2, x plus 2 times h. And again, you'll notice I have h in every term, and so those h's will cancel out. Now all that's left to do is take our limit, and we can see here, now h going to 0 is not problematic. If h goes to 0, notice my function does not become undefined. That h in the term there will go to 0, but that just leaves me with a negative 6 over x plus 2 times x plus 2, or our f prime of x, so our function's derivative, is going to be negative 6 over x plus 2 squared. Okay, so let's look at some other examples of the derivative. Okay. In this case, let's look at f of x equaling 3 square roots of x minus 4. The idea is we still want to do the same thing. We still want to find the derivative using the definition, so using that limit. The difference again here is that we're using a slightly different function. Okay. So again, we'll start out the same way. So f prime of x will equal the limit as h goes to 0, f of x plus h minus our f of x all divided by h. Okay. Now this one is a little trickier than our last two examples because here we're no longer dealing with a nice rational function or a nice polynomial. That square root makes it a little difficult because I can't just combine them as they are. I need to somehow get rid of those roots because as long as those roots are in there, I'm not going to be able to combine those two terms. So here, what we'll do is we'll use the conjugate to rewrite. And again, if you remember the conjugate, says I'm going to take both of the functions I already have, meaning the square roots that are already there, and I'm going to multiply by those same roots, but with the different sign between them. Okay. Now again, because I'm looking at a rational function, meaning the h in the denominator, whatever I do to the top, I have to do to the bottom, so that my function has not changed. Now, just like before, I'm going to algebraically manipulate this by multiplying things out. So this is where your FOIL comes back in. So I'll limit as h goes to 0. I'm going to go ahead and multiply that across. So we'll get a 9x plus h minus 4 minus that middle term plus the middle term. Those middle terms will cancel out. So I'll get a minus a 9x minus 4. All over that denominator. Now again, I'm back to just a rational function, so keep simplifying. So notice the 9x's will go away, the minus 36 and the plus 36 will go away, so I'm just left with a 9h on the top. On the bottom, I still have the roots. Okay. Again, I am back to the step where I have an h in every term, and so those h's can cancel out. Now I can take my limit. So as h goes to 0, again, just that term in there, that little h will go to 0. And so notice I'll have the same thing. You get a 9 over a 3 times the square root x minus 4 plus a 3 times the square root of x minus 4. I can factor that 3 out, and notice it'll cancel with part of the 9. And so I'm just left with 3 over 2 square roots of x minus 4. Because now that the roots are the same, I can combine them, and so there is my derivative. Okay. Now again, what that derivative tells me is I am looking at a function. So for any point I get in there, this instantaneous rate of change is giving me the slope for the entire function. If I put in a particular x value, it'll give me the slope at a particular point for this curve. Okay. So in this next example, we're going to look at that. We're going to take this function, so g of x equaling 3x squared minus 4 over x, and we want to find the slope at the point when x is 1. We start out the same way. So first thing I need to do is find my slope function. So here we're going to look at g prime of x. G prime of x tells us it's the limit as h goes to 0, 3x plus h squared minus 4 over x plus h minus my f of x, 3x squared minus 4 over x. That whole thing divided by h. Now notice at this point I haven't used the 1 yet. Okay. I'm going to get my slope first and then plug in my value. Okay. So to get my slope, I need to simplify. Notice here I have two types of functions. This is actually a combination of the first two examples we did. I've got a polynomial piece and I have a rational piece. The easiest way to work with these is to treat them separately. Okay, so I'm going to work with the polynomial piece. And separately, look at the rational piece. So again, for the rationals, I'm going to have to get a common denominator. Be careful of your minus signs. The minus of minus means that 4 over x is going to be first. So I'm going to need to multiply that by a 4x plus h. And then here, minus the 4 times the x, all over x plus h, x, and that h from the denominator. You may have to pause this and look at that a little closer, but you should end up with this expression. Okay? From there, I can go ahead and simplify. So again, some things will cancel out. So my limit as h goes to 0, my 3x squareds will go away, so I have a 6xh plus 3h squared all over h. Over here, when I combine terms, we'll see that the 4x's will go away. So I'll have a 4h over my common denominator. In both cases, I am now down to a point where I have h's in every term. So I can cancel out that h. So my limit for the first one is going to be of 6x plus 3h. And for the second is going to be 4 over x plus h times x. Now taking my limit, we'll see that as h goes to 0, this first piece will go to 0. So the 3h goes to 0, I'm left with just a 6x. And over here, as h goes to 0, I'm just going to be left with an x times an x on the bottom. So I get a 4 over x squared. This is my g prime of x. Okay, so there's my function for the derivative. Now again, in this case, we wanted to find that function's derivative at the point 1, meaning the slope of the tangent line when x is 1. So here, all we're going to do is plug in that value. So g of 1, or the slope of the tangent line at 1, is going to be the 6 times 1 plus the 4 over 1 squared, or in this case, 10. In our last example, we're going to do the same thing, but we're going to use the alternate method. Okay. So if you look in your book, they give you two different forms to find the derivative by the definition. If I'm looking for just by the definition, this is exactly what we've done in the last 4 examples. If I want to use the alternate method, what that's saying is I'm going to take my g prime, and now because I'm looking at a slope at a particular point, it's going to be the limit as x goes to x naught of g of x minus g of x naught all over x minus x naught, where x naught is your point. Okay, in this case 4. Again, this instantaneous rate of change should look vaguely familiar from the last section. Okay. So for us, in this case, if I want g prime of 4, there should be an x naught there, this is going to be the limit as x goes to 4 of g of x, which is 2 over square root x plus 5, minus g of 4, which is 2 over square root of 4 plus 5. All of this divided by our x minus x naught. Okay. So from here, we want to go ahead and try and simplify this. Okay. So again, just like before, I'm going to start by getting rid of the complex fraction. Okay. Now notice on that second fraction in the numerator, we can simplify that down to 2 over the square root of 9 which is just going to be 2/3. Okay? So here, you can think of that as just 2/3. We're going to use that when we go ahead and rewrite this. So again, to rewrite, I need to get a common denominator, which is going to be 3 times that root. So we'll have a 6 minus 2 square roots of x plus 5. So cross multiplying to get that common denominator. 3 square roots of x plus 5 times the x minus 4. Okay. Now again, just like before, I've got this root that I need to somehow deal with, because that x minus 4 isn't going to work there. And again, to combine terms, I need to somehow deal with that root. So just like previously, we're going to go ahead and multiply through by the conjugate. And again, once we do that, we can FOIL this out. We'll see we get a 36. Again, the middle terms will cancel, so when I do the inner and the outer, those will cancel out. Minus a 4 times the x plus 5. All over this lovely denominator, 3 square roots of x plus 5. X minus 4, 6 plus 2 square roots of x plus 5. Now comes some simplifying. So again, on the top we can see we've got a 36 minus 20, which looks like a 16 minus 4x. Okay. I wrote that, but I'm going to erase it here in just a second because I want you to notice I can pull a 4 out of that, and what I'm going to get is a 4 minus a 4 minus x. Sorry, 4 times a 4 minus x. That's my numerator. And then on the bottom, again, I have these roots and other terms. And at this point, you should notice that x minus 4, which is the problem piece, I can cancel out. There's a sign change, meaning 4 minus x and x minus 4, but aside from that, I can cancel those out. Okay? Which means now I can actually plug in that 4, because I no longer have a place in the denominator that's going to go to 0. So if I plug in that 4, it looks like a negative 4 over 3 times the square root of 9. That term is gone. A 6 plus 2 times the square root of 9. And we can simplify that down. So we'll get a 3 times 3, which looks like a 9. And a 6 plus 2 times 3, which is 6, so that's a 12. So our g prime of 4, meaning the slope of the tangent line at x equals 4, is going to look like a negative 1/27. The alternate method can be used anytime I can use the definition of the derivative. Okay. Again, both of these give the same thing. It's just in one case, once I get the derivative, I have to do something else to get the slope at the particular point. Whereas if I use the value in the alternate method, it's all done in one stage. Okay. You have your options. There are going to be some problems where it specifically asks you to use the definition, which means your limit in this fashion, and there are going to be some problems that ask you to specifically use the alternate, which would be something like this. Every problem is going to be a little bit different just because of the type of function that you're looking at. But there's how we find our derivative algebraically.